Hello and welcome to our guide, The Quest for Insight, Navigating High-Dimensional Data. In today's world, data complexity is skyrocketing. We are no longer dealing with simple tables. We are drowning in data points that have thousands, sometimes millions of features, such as high-resolution images, detailed genomics reports, or massive text corpuses. This complexity brings us face-to-face with a fundamental obstacle in machine learning known as the curse of dimensionality. This phenomenon causes models to slow down, overfit, and become computationally expensive. The entire purpose of this presentation is to equip you with the knowledge and practical techniques required to tame this curse. We will explore how to identify the true, lower-dimensional structure hidden within your data, enabling us to build faster, smarter models and ultimately unlock clearer, more actionable insights. By the end of this session, you will have a comprehensive toolkit to simplify your most complex datasets. Let us begin by quantifying the core obstacle, which we call the modern data challenge. More features, more problems. It has become common for real-world machine learning problems to involve thousands or even millions of features for each training instance we process. This massive explosion of features comes with critical consequences. Firstly, it makes model training extremely slow, often requiring vast computational resources and days or weeks of processing time. Secondly, it can make the task of finding a robust, generalizable solution much harder. This difficulty in modeling and computation resulting from high feature count is precisely what we define as the curse of dimensionality. Consider the classic example of the MNIST dataset, a foundational benchmark in machine learning. Each handwritten digit is represented by a 28 by 28 grid of pixels. This means that every single data point is a 784-dimensional vector. Our challenge is to find the meaningful signal, the actual shape of the 8, amidst all the noise across those 784 feature dimensions. We need effective methods to drastically reduce this complexity without losing the crucial signal. The primary reason the curse of dimensionality is so hard to manage is that our human intuition, which is honed by a lifetime spent in 3 spatial dimensions, completely fails us when we try to imagine high-dimensional space. We can easily conceptualize a 0-dimensional point, a 1-dimensional line, and even a 3-dimensional cube. We can draw the outline of a 4-dimensional tesseract, but grasping what that volume truly means is nearly impossible. This mental block leads to deeply counterintuitive mathematical results. The most profound of these results is that in high dimensions, most data points are extreme. Let us make this tangible using probability. In a simple 1 by 1 square, there is a very small 0.4% chance that a random point will fall within 0.001 units of a border. The points tend to cluster near the center. Now, scale that same calculation up to a 10,000-dimensional unit hypercube. The probability that a random point lies close to the border explodes to over 99.999999%. The center of this massive hypercube is almost completely empty. Data points sit exclusively in the vast periphery, acting as isolated, extreme vectors. High-dimensional space is defined by 4 practical consequences that make it vast, sparse, and extremely misleading for machine learning models. The first consequence is sparsity. Because the space is so immense, training instances are likely to be extremely far away from each other. This dramatically reduces the effectiveness of distance-based methods, such as k-nearest neighbors, because calculating meaningful distances becomes almost impossible. The second is overfitting. With so much empty space for the model to maneuver, models can more easily fit noise and spurious correlations instead of capturing the underlying true signal. Consequently, regularization techniques become absolutely critical when dealing with wide data. The third consequence is unreliable predictions. Since any new instance you feed the model is likely far from any training point it has ever seen, the model is forced to make large, unreliable extrapolations. Finally, and perhaps most crushingly, we face exponential data needs. The number of training instances required to maintain a consistent, effective data density grows exponentially with every added dimension. To highlight the failure of distance, look at the average distance between 2 random points. It jumps from 0.52 in a unit square to a staggering 408.25 in a 1 million dimensional hypercube, showing how distances inflate and lose utility. Fortunately, the curse of dimensionality has a fundamental flaw we can exploit, and that is the manifold hypothesis. This key insight is what makes dimensionality reduction possible in the real world. The hypothesis states that most real-world high-dimensional datasets do not actually fill up the entire potential space. Instead, they lie close to a much lower dimensional structure known as a manifold. This is the explanation. In most real-world problems, the training instances are not spread out uniformly across all dimensions, as that would imply total randomness. Instead, they are highly constrained by the nature of the data, effectively squeezing the data into a lower dimensional structure embedded within the high-dimensional space. Let us revisit MNIST again. If you were to randomly generate all 784 pixel images, only a ridiculously tiny fraction of them would actually look like a proper handwritten digit. The constraints inherent in a recognizable digit, connected lines, white borders, centering, dramatically reduce the degrees of freedom available to the data. These constraints force the data points onto a low-dimensional surface, the manifold, that represents valid handwritten digits. Our entire goal in dimensionality reduction is to effectively unearth and extract this hidden manifold. When approaching the task of finding this underlying structure, we rely on two core philosophical approaches that guide our choice of algorithms. The first is projection. This philosophy assumes that the data lies on or near a simple lower dimensional subspace, which we can visualize as a flat plane. Under this assumption, we simply project the high-dimensional data straight down onto this subspace. This approach is mathematically linear, fast, and very common when the underlying structure is relatively flat or linear. Principal component analysis, or PCA, is the perfect example of a projection technique. The second philosophy is manifold learning. This assumes the data lies on a complex lower dimensional manifold, a surface that might be bent, twisted, or coiled, much like a Swiss roll. Since simple projection would merge distinct parts of the twisted structure, the goal of manifold learning is to unroll the manifold to reveal its true, simpler structure. These techniques are computationally more complex and slower than projection methods, but they are absolutely essential and powerful for highly nonlinear data that cannot be flattened without losing critical information. This slide clearly illustrates the critical pitfall of relying solely on simple projection when the underlying structure is nonlinear. On the left, we see a coiled manifold, which has a meaningful structure where the red points are distinct from the yellow points based on their location on the coil. If we attempt a simple projection, meaning we squash the data straight onto a flat plane, we end up merging or overlapping distinct parts of the data. Notice how the red and yellow points become indistinguishable in the center of the projected blob. This is known as the information loss of projection, and it happens when the underlying subspace twists and turns. Critical details about the ordering and distance of the data are lost. This failure motivates the need for the second philosophy, unrolling the manifold, as shown on the right. By using a manifold learning technique, we preserve the distinct layers and their internal relationships, even when flattening the structure. This ability to handle nonlinearity is why advanced techniques are necessary when simple linear projection fails to preserve the critical differences in your data. Let us dive into the most popular and widely implemented algorithm in dimensionality reduction, principal component analysis, or PCA. PCA is rightfully known as the workhorse of the field. What exactly is PCA? It is a projection-based algorithm that aims to find the optimal lower dimensional representation of the data. PCA is fundamentally a two-step process at a high level. First, the algorithm identifies the hyperplane, which is the lower dimensional flat subspace that lies closest to the overall data cloud. It calculates this plane to minimize the average square distance from every data point to the plane. This ensures that the hyperplane is the best possible linear fit for the structure. Second, once the optimal hyperplane is defined, the algorithm simply projects every data point onto that new surface. If the original data lived in X, Y, Z space, and we chose a two-dimensional hyperplane, the result is a reduced dataset that now lives in a new two-dimensional space defined by the projected axes, Z1 and Z2. How does PCA mathematically determine the closest hyperplane? Its selection process is guided by a powerful and elegant principle. It seeks to preserve the maximum amount of variance. Variance in this context is synonymous with information. PCA looks for the projection that spreads the data out as much as possible, ensuring that the relationships and distinctions between points are maintained. We can understand this best with the shadow analogy. Think of your shadow on a sunny day. When the sun is directly overhead, your shadow is a small, compact blob. This represents low variance, and you have lost all distinguishing information about your form. Now, imagine sunrise. When the sun hits you from the side, your shadow stretches out and is large, retaining a high variance projection that clearly looks like you. PCA strives for the sunrise shadow. The charts on the right illustrate this. The projection that maximizes the variance spreads the points out, keeping them distinguishable. Conversely, the projection that minimizes variance squashes the data into a useless cluster. PCA ensures we select the axis that maximizes information retention. To perform dimensionality reduction using PCA, we need to find the principal components, which are the axes that maximize this variance. What is a principal component, or PC? A principal component is simply a unit vector, or an axis, in the data space. The first PC is defined as the axis that accounts for the largest amount of variance in the entire dataset. Once that is established, the second PC is chosen to be strictly orthogonal, meaning perpendicular to the first, and it accounts for the largest amount of the remaining variance that was not captured by the first. This process continues, finding subsequent components that are orthogonal to all previous components and capture the maximum amount of residual variance, for as many dimensions as the dataset possesses. The mathematical engine powering PCA is a standard matrix factorization technique called singular value decomposition, or SVD. SVD decomposes the training data matrix X into three separate matrices: U, sigma, and V transpose. The key insight for practitioners is that the matrix V contains the unit vectors that precisely define all the principal components we are looking for. Putting PCA into practice is highly accessible thanks to robust libraries like scikit-learn. Implementing PCA involves importing the PCA class from sklearn, decomposition. Once imported, we instantiate the PCA object. In our example code, we are setting the parameter n components equal to 2, meaning we want to reduce the data down to 2 dimensions. We then use the fit transform method on our data matrix X, which performs the decomposition and the projection in one step. The two most important outputs we must understand are PCA.components underscore and PCA.explained variance ratio underscore. The components attribute holds the actual principal component vectors, which define the new axes. The explained variance ratio attribute is even more crucial. It is an array that tells us the proportion of the dataset's total variance that lies along each respective principal component. Look at the example output provided. The array shows 0.82 and 0.108. This tells us that approximately 82% of the variance lies along the first PC, and about 11% lies along the second. The remaining variance, roughly 7%, is distributed across any subsequent PCs, which likely carry little useful information and can be safely discarded. One of the most practical and crucial decisions in applying PCA is choosing the optimal target number of dimensions, which we denote as d. We have 3 excellent methods for selecting this value. First, you can choose based on a target variance. Instead of arbitrarily picking a number, you instruct the PCA object to select the minimum number of components necessary to preserve a desired percentage of variance. For instance, 95%. This is often the safest and most robust method. Second, we use the elbow method. This involves plotting the cumulative explained variance as a function of the number of dimensions. You look for the elbow in the curve, which is the point where the curve starts to level off dramatically, indicating that adding further dimensions yields rapidly diminishing returns. For the MNIST example shown, the elbow suggests a good cutoff around 150 dimensions. Third, if PCA is a preprocessing step for a supervised task like classification, you should treat n components as a hyperparameter and tune it. Use cross-validation to find the value of d that results in the best overall performance for your downstream supervised model. In the MNIST plot, to hit 95% variance, we only need d equal to 154 dimensions. To demonstrate the tangible power of PCA, let us review a case study focused on compressing the MNIST dataset with 95% fidelity. The setup begins with the original MNIST dataset, where each image contains 784 features, corresponding to the 784 pixels. We then apply PCA, specifically setting the n components parameter to 0.95, which instructs the algorithm to retain the minimum number of components necessary to preserve 95% of the variance. The result is genuinely impressive. The dataset is reduced from 784 features down to just 154 features. This means the new dataset is now less than 20% of its original size, resulting in enormous benefits for storage, memory usage, and model training speed. Crucially, we lost only 5% of the total variance, meaning we retained 95% of the information content. The visual comparison shows the reconstructed images built from the 154 features. There is only a slight loss in image quality, perhaps a minor blurring, for a massive reduction in complexity. This showcases how PCA provides immense efficiency gains with minimal data loss. While standard PCA is powerful, it faces significant challenges when applied to extremely large datasets, because it requires the whole training set to be loaded into memory simultaneously, which is often impossible. To handle massive data, we rely on scaled variants of PCA. The first solution is randomized PCA. This is a stochastic algorithm that finds a fast, highly accurate approximation of the principal components without calculating the full SVD. You should use randomized PCA primarily when the number of dimensions you intend to keep, d, is much smaller than the original number of features, n. It significantly speeds up calculation in these scenarios. In scikit-learn, this is implemented by setting the SVD solver parameter to randomized. The second scaling solution is incremental PCA, or IPCA. IPCA solves the memory problem by splitting the training set into smaller mini-batches. This allows PCA to run on datasets that are too large to fit in memory, processing them piece by piece. IPCA is also the standard tool when you need to apply PCA online, meaning you feed it new data sequentially as it arrives. In scikit-learn, you use the incremental PCA class and feed it data batches using the partial fit method. For datasets facing truly extreme dimensions, perhaps tens or hundreds of thousands of features, such as those found in highly detailed images or complex genomic profiles, even the optimized randomized PCA can still be too slow. This requires a truly radical and often surprising alternative: random projection. The solution is simply to project the data to a much lower dimensional space using a completely random linear projection matrix. This idea sounds counterintuitive, as we traditionally seek optimal axes like PCA. However, the theoretical underpinning for its effectiveness is sound, rooted in the Johnson-Lindenstrass lemma. This mathematical proof shows that a random projection is very likely to preserve the distances between points fairly well. If two instances were similar in the original high-dimensional space, they will remain similar in the lower dimensional space after the transformation. The key benefit, and the reason this method is so powerful for extreme dimensions, is algorithmic complexity. The algorithm's speed depends only on the number of samples, not on the massive number of original features, n, offering a substantial complexity advantage. Random projection is valued primarily for its speed and simplicity in handling massive feature counts. The process is straightforward. First, you determine the target number of dimensions needed based on the number of samples, and a required tolerance level epsilon for distance preservation. Second, you generate a random matrix with the shape of d rows by n columns. Third, you project the data x by simply multiplying it with this random matrix. Scikit-learn offers two primary implementations. The first is Gaussian random projection, which is the standard implementation using a dense random matrix. The second, and usually preferred, is sparse random projection. In this implementation, the random matrix is sparse, meaning most of its entries are 0. Using a sparse matrix drastically reduces memory consumption and allows the algorithm to run much faster, all while achieving comparable quality and distance preservation. For instance, for a dataset with 5,000 instances and 20,000 features, a sparse random matrix might use only about 25 megabytes of memory, compared to approximately 1.2 gigabytes required for a dense one. This immense efficiency gain makes sparse random projection a critical tool for extreme feature reduction. We now move back to the nonlinear realm with our first true manifold learning technique, locally linear embedding, or LLE. LLE is a powerful nonlinear dimensionality reduction technique that does not rely on projections, making it exceptionally good at unrolling complex, twisted data manifolds. LLE operates under a central assumption that the manifold is locally linear. This means that although the global shape is curved, any single training instance can be accurately represented as a linear combination of its immediate neighbors. The algorithm works by modeling local relationships. For each training instance, LLE determines how it relates linearly to its k nearest neighbors by finding a precise set of reconstruction weights. For example, if point A is between points B and C, it finds weights such that it equals weight B times B plus weight C times C in the second stage. LLE aims to preserve these relationships. It then searches for a low-dimensional representation of the data where these exact same reconstruction weights hold true. LLE is particularly effective at unrolling severely twisted manifolds, provided the dataset is not too noisy. LLE's efficacy is best demonstrated by its ability to unroll the Swiss roll dataset, a classic benchmark for manifold learning. Here, we see the 3D spiral successfully flattened into a clean 2D representation. The implementation in scikit-learn is simple, requiring the definition of the target number of components and, crucially, the number of neighbors, k. The success of this algorithm is evident. The Swiss roll is completely unrolled, and the local distances between neighboring instances, represented by the color gradations, are perfectly preserved. Points that were neighbors in 3D are still neighbors in 2D, however. LLE does suffer from important limitations. Global distances are not preserved. Notice that the result is not a perfect, undistorted rectangle. Furthermore, and most practically, LLE scales poorly to very large datasets. Its computational complexity often grows quadratically with the number of samples, or OM squared. This means LLE is generally reserved for datasets where precise local structure preservation is critical and the number of instances is manageable. While PCA and LLE form the backbone of dimensionality reduction, a broader toolkit exists, offering specialized approaches tailored to specific goals. Multidimensional scaling, or MDS, is a technique that reduces dimensionality while striving to preserve the distances between all instances, making it useful when the global spatial arrangement is important. ISOMAP, or isometric mapping, connects nearest neighbors to construct a graph representation of the manifold, and then preserves the geodesic distances, which is the shortest path along the graph surface, effectively flattening the manifold. t-SNE, which stands for T-distributed stochastic neighbor embedding, is primarily excellent for visualization tasks. It is designed to keep similar instances close together and force dissimilar instances far apart, revealing tight, coherent clusters. Importantly, t-SNE is generally not recommended for data preprocessing prior to model training. Finally, UMAP, or Uniform Manifold Approximation and Projection, is a popular, modern alternative to t-SNE. UMAP offers improved performance, better preservation of both local and global data structure than t-SNE, and superior scalability, making it a very strong candidate for large visualization tasks. This slide provides a powerful visual synthesis, demonstrating how different dimensionality reduction tools yield different views of the exact same data. We applied three major algorithms, MDS, ISOMAP, and t-SNE, to the Swiss roll manifold. The MDS result successfully flattens the roll but attempts to preserve the global curvature. Because it tries to keep the far points far apart, the center remains compressed, reflecting the high original density. The ISOMAP result, being a true manifold learner, completely unrolls the data, successfully dropping the global curvature to create a flat, even representation. The t-SNE result, optimized for local visualization, flattens the roll but strongly amplifies local clusters, essentially tearing the surface apart slightly to ensure distinct groups are clearly separated. This demonstrates a critical lesson. There is no single best technique. The optimal choice depends entirely on your specific downstream task. Do you need to preserve global structure for regression, focus purely on local clusters for classification, or simply unroll the manifold for interpretation? Your ultimate goal must dictate your choice of tool. To help you navigate the rich but potentially overwhelming toolkit, here is a practical framework for choosing the right tool for your specific challenge. We start at the top by identifying your primary goal. Is it visualization or preprocessing? If your goal is visualization, consider t-SNE for tightly defined clusters or UMAP for preserving local and global structure. If your goal is preprocessing, we typically start with the most basic and interpretable linear approach, PCA. PCA is a fast, powerful, and excellent baseline. However, if PCA is too slow, perhaps because your dataset is extremely high-dimensional with millions of features, you should jump directly to using random projection for its massive speed advantage. If you have labeled data, meaning you know the class of each instance, and your goal is to maximize the separation between those classes, then you should use the supervised technique, linear discriminant analysis, or LDA. Finally, if PCA performs poorly, indicating that the data is not linear, and you suspect a complex nonlinear structure or manifold, that is the time to explore powerful manifold techniques like ISOMAP, LLE, or the highly versatile UMAP. In conclusion, dimensionality reduction is much more than just a simple preprocessing step aimed at speeding up model training. It is a powerful conceptual lens for finding the true, inherent, underlying structure in complex data. The curse of dimensionality highlights that the vastness and sparsity of high-dimensional space often render our problems intractable, leading to slow processing times, memory exhaustion, and unreliable models. By skillfully navigating this vast space with the appropriate tools, ranging from linear methods like PCA and random projection, to powerful nonlinear manifold learning techniques like LLE and UMAP, we gain the ability to turn those intractable problems into highly tractable ones. This enables us to build models that are not only faster and more efficient computationally, but also smarter, more robust, and ultimately helps us unlock clearer, more fundamental, and more actionable insights from the very core of our data. Embrace dimensionality reduction to transform complexity into clarity.